Hello, everybody. Let us resume our discussion on coherent detection of electromagnetic wave. Remember that we first talked about a single antenna. We used one antenna to converge the electromagnetic wave coming from a rather larger area of the incoming wavefront to a dipole. So, this is often called single antenna or single dish telescope. For this, we looked at this antenna beam pattern, which was having some directional sensitivity, and we made this polar plot of the antenna beam pattern. It's the main lobe here and the side lobes, and you can have more side lobes. I'm just drawing two of them. And the directional sensitivity of the antenna, we wrote down that where it goes to the first zero, so in this direction, this particular direction, the directional sensitivity is 0, and here it is maximum. So this if I call delta theta. So if you remember, delta theta was given by, for a circular aperture, it was 1.22 lambda by the diameter of the dish. This pattern we called A as a function of the direction n cap. So this is the directional sensitivity of the dish. And if I want to see or measure the structure of intensity in the sky, what I had to do is, we said, is that, say, imagine that we want to measure the intensity coming from different directions in this part of the sky. This box represents the sky. So what you do is, imaginary grids. You think of imaginary grids in this. These are imaginary lines, and each of these are of width delta theta, say, by delta theta. So that is, in one observation, when my telescope is pointing towards this, the center of this grid, so n cap is towards the center of this grid, then I will get the total intensity of the electric field that is because of this part of the sky. Then what I do, so I write that down, and then I change the direction of the telescope to this part of the sky, and keep on doing this. And that is how I calculate, or I made the image of the sky, if you wish. Once I know the electric fields of different positions, and I can calculate the intensity at different directions, like for the center of each of these grids, and then I can find out how the intensity is distributed over this region in the sky. You see, that's all. It's a very time consuming process because you have to do the observation many times. And we were developing a way of actually measuring the distribution of intensity by just looking at one direction in the sky. This is also limited by resolution. If I for so this is also true for optical wavelengths. You do exactly the same thing. We'll come to the incoherent detection after this discussion is over. Then you will see that this, up to this, what we have discussed, it's exactly the same thing. Now the resolution is limited. Resolution we can achieve is limited by the largest antenna diameter, or the largest antenna that we can make. This d is the antenna diameter, d over here is the antenna diameter. So the largest we can make, it is limited by that. So then what we said is, okay, so we said that we will look at a different quantity, which we still don't know why we are looking at it, but at the last part of the last lecture, we looked at the spatial coherence function. Spatial coherence function of the electric field at the face of the earth, if you wish. So this is measured by pair of antennas. And it's measuring the electric field and then squaring it. So this can, at least at this stage, can be done only with coherent detection, only with the waves where the coherent detection is possible, like the radio cases. So this is E at x1, electric field measured at x1, and E star at x2, and we take this what we call the average, and this was given by the following integral. This we arrived at the end of last discussion. I being the intensity of the sky in the direction n cap. So let me write it this way: n cap dot d by lambda. Okay, so this is the spatial coherence function, and you can see, just like the temporal coherence function, this also depends on d only. So d is nothing but x2 minus x1, which is the difference between the two particular positions of the antenna. And let us define a vector capital U, not small u, rather capital U, which is d in terms of the observing wavelength lambda. Okay. So this entire quantity I can write in terms of that u only. So you see that this is only a function of u. We call it V. So V stands for, the spatial coherence function is called visibility. Okay. So u is nothing but the vector d, which is the separation between physical position of the two antennas in terms of the observing wavelength lambda. This is a very celebrated uh, theorem. By the way, this integral is over all solid angle omega. So this is a very celebrated theorem called the Vancitogenica theorem. Okay, so we'll spend some time discussing this theorem now. You see, what we are doing here is that we are looking at a patch in the sky, and the sky is like a spherical dome. So let me draw this part of that spherical dome here, like this curve, and then we are looking at this small patch in the sky. And I have my antennas in the earth, on the face of the earth, and these I draw like this. They are all looking at that part in the sky. That part in the sky is very far away, so these antennas are looking in this way. So these two lines that I have drawn here is supposed to be parallel because that patch in the sky is very far away. So n cap I can think of this, the n cap is measured compared to the direction towards the center of that patch I am looking at. Okay, so that patch is on the sky is nothing but what I have shown over here. So that is the entire region of the sky that you want to measure. okay, of the intensity of. And as we know already that if we are looking at, so my antennas are always following that patch, so then this patch gives a solid angle of 1.22 lambda by d square. So this patch in the sky is nothing but this shaded region here, so which is the entire thing that I can collect electric field of if I'm pointing my antenna towards the center of this grid. This is the exact same thing I'm doing here. That small patch is that small grid. All right. So what we do is we define a Cartesian coordinate system where if I am looking at this way, so this is essentially my line of sight, which we introduced the phrase earlier. So this is my line of sight. So this I consider as my z axis, and then my x and y lies in that, in the plane of that patch. So x and y will be in the plane or parallel to the plane of that patch. So I can say x this way and y this way. Okay, so this where is z equals to 0, it's up to your choice. You usually choose it at the antenna, but really that doesn't matter. We'll see that shortly. But this is the coordinate system that I am looking at. So one important thing here is that the coordinate system z axis is always fixed with the center of the region of the sky I am looking at. So if this region of the sky have a galaxy, I am fixing the z direction always at the center to the galaxy. So as the sky rotates, as the earth rotates, the sky appear to rotate. At some point later in time, this part of the sky will be here. So my antennas will now change their direction. So they will look like this. And then this is the direction they will be looking at. So line of sight now with respect to a coordinate in the earth has changed, but that line of sight vector is still fixed to the center of my field of view. So that part is called the field of view. So this is my field of view. And we have already seen it is given by 1.22 lambda by d, which is related to the information or diameter of each antenna. And the distance between these two antennas is given by this vector d. The antenna can be anywhere in the plane of the earth, so that distance is d. Okay, and now you see that my coordinate system has rotated. My coordinate system here will have z in this way, and will have x and y in some plane in the sky perpendicular. Okay, so my coordinate system is rotating as the time progresses, but with respect to the sky, the coordinate system is fixed. Because we are interested things in the sky, so it is better to fix or define a coordinate system that is fixed with respect to the sky. That is what we have done here. Okay, so now what is this n cap? Remember, n cap is the direction of any point in this source. So n cap can point to somewhere here, for example. And you see that n cap now I can write in terms of its components along my xyz coordinate system. So these, because it's a unit vector, so these are called the direction cosines, is the projection of the unit vector along L, M and N. And because it's a unit vector, this component should add up to 1 in this following way. Right? So N is, there are not three independent quantities, there are only two independent quantities. All right, that is fine. Now you see, this is all right. N cap is given by L square plus M square equals plus N square equals to 1. we also recognize that n will have the maximum thing, because the amount you displace, the field of view is usually very small. Field of view for GMRT, as we calculated last time, will be few arc minutes, say 30 arc minutes or so. So that is reasonably small. So because of that, n will be maximum. It's almost be 1. L and m will be rather smaller. But that's all right. That will come to later. What I do is I write my u also in the same coordinate system. So u becomes, the three components is u, v, and w. Okay. So what are these three components? It's the three component of d by lambda along the x direction here is u, d by lambda along the y direction is v, and d by lambda along the z direction is w. Okay. So if I do that, then I can write this n cap dot d by lambda, which is u. Okay. Also, one can calculate, I am not doing it here. So dn cap, you can see that it can be written as dl dm, integration over only two variables because the other is not independent. Okay. So if I use all these, I can now write the Vancitogenica theorem. So my v in terms of uvw is now integral of dl dm. The double integrals, I'm just writing one integral sign here. An cap is alm, in cap is ilm, multiplied by e to the power I 2 pi ul plus vm plus this entire 1 minus l square minus m square times w. Okay, so that is my Vancitogenica theorem now written in terms of this particular Cartesian coordinate system. We observe also that, as we said, that this ALM, which is the extent of ALM, is given by this 1.22 lambda by d, and for an antenna like GMRT, that extent is rather small. So ALM is a function. If I plot it with respect to L and M, it goes to 0 very rapidly, which means that my L square plus M square is much smaller than 1. And if I take that assumption, so this is case for most telescope, this is true. There are telescopes where this is not true, so then we have to deal with this entire expression. And if you actually want to calculate things precisely, then also you have to deal with this entire expression. But let us assume for the time being that L square plus M square is much less than 1. Then what happens? Then root over of 1 minus L square minus M square can be approximated as 1. And if I do that, then V U V W, this becomes, so let's see what it becomes. So 1 minus L square minus M square in square root just becomes 1. So this is just dl dm. I have ALM here and ILM. In the phase, I have 2 pi UL plus VM. And the other part, so this is 1 into W. So it's not a function of L and M anymore, if I have taken that approximation. So this is I 2 pi W. So even I can define now V uv, if you wish, I can call this V prime uv, which is e to the minus I 2 pi w times V uv w. And what is that? This is this entire thing in the integral. Remember, this is only true when ALM goes to 0 very rapidly as ALM increases. So that assumption you have to keep in mind, which holds for most of the telescopes. And if you look at it carefully now, V prime is just a Fourier transform of this. So V prime, let me keep that in the left hand side, Fourier transform this quantity. So what we can say is that, so how have we achieved this? We have calculated this by correlating the electric field as measured by two different antennas, right? So that is, this is something that we can measure. So V is the visibility. So this is a little modified, but remember that this is what we call the visibility. This is something that we can measure. And how we measure this? We measure using two antenna pairs or a pair of antennas. So we can say a pair of antenna measures one Fourier component of the, I will say, spatial intensity distribution, because ALM is something of your antenna, you will know that. Specific intensity, sorry. So this we understand. So this is coming from the Vancitogenica theorem. So if we have many pairs of antenna, we in principle we can get all the Fourier components inverse Fourier transform. This will give us the visibility. I'm sorry. This will give us the I. It will give us I times A, but A I already know, so I can get I from it. Well, of course, this is itself is a big business because it's quite complicated. Turns out to be quite complicated. But the idea is the following. So we can measure the visibilities by measuring the electric field from two different antennas. Those one pair of antenna measures the Fourier component of the specific intensity at u equals d by lambda. D is the antenna separation. So if I change the antenna separation, which obviously I will not be able to move the antenna around, though that is what people did in the early days. But if you can have many antennas, so with different antenna separations, you measure different pairs and you can get many Fourier components. And if you get many Fourier components, you will be able to measure the inverse Fourier transform easily. There is one more interesting thing that happens here. So to get, so let's ask the question: how many Fourier components can we make? Can we measure? So one of the early interferometer is, so this is using, so this is essentially this spatial coherence function or visibility is essentially the interference pattern of the antenna. So because of that, it's called an interferometer. In interference, you essentially do the exact same thing. It's nothing but what we have calculated is the interference from two circular apertures. Like we have studied, you have studied earlier the interference between two slits, double slit interference pattern. This is double circular aperture interference pattern is the visibility. Okay, so these are called interferometers because they work in radio. So this class of instruments or telescopes are radio interferometers. Okay, so now let's list a few interferometers. So one early interferometer that came into picture is called VLA. And for this interferometer, I request you to look at all these interferometers by going to their websites. There are a lot of informations and physics available in there also. So for this interferometer, the maximum baseline that you can achieve, so D, modulus of D, is about 30 kilometer. And D, which is the diameter of these dishes, is 25 meter. Okay. The class of interferometer VLA is it works at certain frequency ranges. For the low frequency, the same class, the largest interferometer is made and maintained at in India. VLA stands for Very Large Array. It's in New Mexico. It's in United States. The Indian interferometer called GMRT, Giant Meter Wave Radio Telescope, where the largest separation is about 25 kilometer. So the farthest antennas are kept 25 kilometer apart. This was in a desert. VLA, GMRT is not in a desert. It's within the farmlands. And the dish is 45 meter. And nowadays, radio astronomy community worldwide, which India is a major part, is planning to make interferometers called square kilometer array. And there are different types of these interferometers which will be kept at different places. So these are called SKA, square kilometer array, and they will have a distance of about, so let me write 100 kilometer here, so it varies for different models, and the dish will be around, it varies for different models as I said, is around say 25 meters or so. So these also varies for different models, so I put exclamatory marks over here. Okay, the largest interferometer that exists is a collection of several dish antennas around in United States of America. It's called Very Large Baseline Array, and it's really very large because this number is 8500 kilometers. Okay, I request you to look at all these interferometer. There are many, and search the internet for these interferometers. Okay, so I can keep on listing this, but let me stop here. Okay, so I think this is enough, so you can fill up these numbers here. Now this column, as we said, gives the part of the sky we can see at a given go. And this is related by this 1.22 lambda by d. We call this field of view. So just like when with our two eyes open we look at the field of view in the horizontal direction, we can see is about 120 degrees. Okay, vertical it is less. So you can look that up for our eye also. So that is much less for these telescopes. It's about less than 1 degree for most of the telescopes. So, but you can see, you can figure out if you look at this list and make this list longer. There are some which I have already written which sees more than 1 degree field of view. Okay. And what is this column gives you? The column with small d, which is the largest separation between any of these two antenna pairs. This gives you the largest Fourier component of I of the specific intensity we can measure. Largest Fourier component will corresponds to, we have discussed is in the last class, always the largest in the Fourier domain corresponds to the smallest in the other domain. So this will corresponds to the smallest angular scale. And hence the resolution of this interferometer is given by, the angular resolution is given by lambda by d. So the largest Fourier component is d by lambda, or I should write d max, which is the maximum baseline by lambda, and lambda by d, which is the inverse of that, is the resolution. Okay, so if I remind you, this vector u is called the baseline vector. Baseline because you can think of a line between the two antennas which is giving this vector. So that's why it's called baseline. Base means it's on the face of the earth. So if I use this formula for the resolution and try to calculate the resolution for these telescopes, so but let's say that resolution at 20 centimeter, so wavelength is 20 centimeter. So you can work out for GMRT or VLA, it will be like 1.5 arc second. And when you go to VLBA, which is enormously large baseline, it will be 68 milliarc second, 0.068 arc second. Okay, so for 20 centimeter, if you go to a smaller wavelength, then this will even decrease. So now you see that we already said that for optical, we can achieve a resolution of 1 arc second from the ground-based observatory if you are not doing very complicated techniques. And the best you can achieve is 0.01 arc second, I guess. It can be a little bit lesser than that now in certain frequencies, certain wavelengths. But with the interferometer here, we are being able to achieve similar resolutions or even better resolutions with radio interferometers. So the problem that was there of this making a dish which is bigger is being solved by placing the dish at different places. Okay. And remember that each pair of these dishes will measure one Fourier component. So what you are essentially doing using this method is synthesizing amounts to synthesis of a single dish antenna. Synthesis means I not really make it, but make use of a complicated technique, which is the technique of radio interferometry, to get the same result that of a single dish antenna of diameter Dmax, which is the largest separation between the two antenna pairs. So for VLB, it is 8,500 kilometers. You have heard of the observation of the shadow of the black hole by the Event Horizon Telescope collaboration. That is also a similar type of experiment. It's a more complicated experiment, but it's also a radio interferometry experiment. And I request you to look at what resolution they have achieved and at what wavelengths. What was the maximum baseline they have used? Okay. So this is the technique of radio interferometry, and this is how you get a very high resolution. One question still remains, that how many antenna pairs do you need to get enough Fourier components? Say each pair of antenna measure one Fourier component. So how many antenna pairs do you need to measure all the Fourier components? So what we are trying to do essentially is I can now draw something we call a baseline plane, where I have this U and V, and I measure the visibility as a function of U and V here. Okay. Remember, visibility is a complex number. If you look at the integral here, the right hand side have all these things. So visibility is actually a complex number, and it has certain properties which I will request you to, I will ask you to calculate in the assignment. But it's a complex number. So you measure one complex number at each point. How many points in this baseline plane should I measure it such that I can do a Fourier inversion? So these two planes are Fourier transform related. And this is my sky plane where L and M varies, and I have my intensity at every point defined in terms of L and M. So how many points should I measure here such that I can reconstruct the intensity by doing an inverse Fourier transform? Now, if I look at these telescopes, so if I call number of antenna, VLA has 27 antennas, GMRT has 30, but usually 27 are operational at a given time. These have of the order of 100 to 150 to 500 antennas which are planned, etc., etc. So I'm not going down the line. And the number of antenna pairs at a given moment, antenna pairs at any moment, at any time, is n antenna, C2, C for combination. So for n antenna equals 30 for say GMRT, this number is 435. So 30 into 19 by 2, which is very small. So you only measure 430.5 points in the baseline plane. Only few points actually. You need many. You need around 10 to the 6, 10 to the 7 points to be able to reconstruct the intensity. So what do you do? So there again lies a clever technique. You remember that this U and V, the components U and V, are in a certain Cartesian coordinate system. And that Cartesian coordinate system we discussed here. And the coordinate, the direction in which you are looking at changes with time. So at some point it is looking at this direction, at some point it is looking at that direction. So let us look at two antenna pairs and try to figure out what will be U and V. And for the time being, so usually U is along the east-west direction. So let us reduce one dimension and we say that our antennas are separated only in east and west direction. So this is one antenna, and obviously the antenna position never changes, at least for these two antennas that we are talking about. And at some point, it's looking at a source which is in this direction. So this is the direction of the source. So my antenna is rotated this way because then only the beam, or what we call the primary beam of the antenna, will look at that direction. Okay. Now what is D? D is this. But how much is U? U is D by lambda, but along a plane which is perpendicular to the line of sight. So this is my line of sight. So remember in my figure where I defined the coordinate system, x and y, x is the direction in which, if I say U lies, it's in a plane perpendicular to the line of sight, perpendicular to z here. So that will be along here. So if the antennas are looking at a certain angle, say theta, with the vertical, then this is cos theta. Can calculate this distance, which I mark with the other color. So this is what is U. This is U, or lambda times U, if you wish. So that is d cos theta. Obviously, as the time progresses, so say I'm looking at a source here, the source is moving along the hemisphere from rise and set. So this is east, this is west. So let me draw it again. So source now is here. My antenna stay at the same place. Their physical distance in the ground remains d, but now it is looking at this, the source which is in this direction. So line of sight is here. So these are the two direction of the antenna beams, and the projection is this much, and the plane perpendicular to the line of sight. Okay, so if I call now this as theta prime, so now U is d by lambda cos theta prime. So what is essentially happening here is, as the time progresses, the position of the source changes in the sky, and the projected baseline, or the baseline components U and V also will change, which will not be shown here. But both of these, and even W, if you have W important in your case, all of these are changes with time. And as the components changes, these points move around in the baseline plane. And that is what gives rise to a lot of points, a lot of Fourier components measured in the baseline plane. And then I will be able to convert it. So remember that we called this aperture synthesis. So this is synthesis of a single dish antenna. So this is what we call aperture synthesis. And this now is aided, aperture synthesis aided by Earth's rotation. So this is called Earth rotation aperture synthesis. Okay. So this is what we will discuss in this in the about radio interferometry and coherent detection here. I have not talked about many things, and it's entirely a subject, and a lot of people still work on the techniques of radio interferometry, uh, including myself. However, it is not possible for us to discuss a lot in 2 lectures. What I request you to look at are all these different antennas, and you can search for these terms also, like Earth rotation aperture synthesis. You can search for Nobel Prizes awarded for this particular technique. So you can imagine how important such a technique is. So I'll stop here today, and in the next lecture, we will discuss about the incoherent detection of radiation.